Thank you, Kathy. So you've just seen my talk, and I'll have questions. So I've been tasked to talk about the evolution and the outstanding challenges in El Nino modeling and prediction. And I thought, given that, it's extremely relevant to start with the first ever El Nino prediction using a dynamical model. This was referred to earlier. This is the model that Ziviak and Marcaine developed in advance of the 1986-87 El Nino. So here on the bottom is the forecast, and on the top is what was observed. So this forecast was made in January of 1986, for the following January. They then wrote the paper and got it submitted in Nature and accepted. So apparently they went around science as well. And this was published in Nature in June of 1986. Clearly the editors of Nature were also a little squeamish about issuing forecasts and put this disclaimer at the end of their paper. But this modeling system actually has gone on to predict quite meaningfully the variability in the tropical Pacific. It's still used today as a research tool and for El Nino prediction. So the winter of 1990-1991, this model predicted some warming but no actual event evolving. A year later, 1991-92, it predicted pretty accurately a moderate El Nino event. Then in 1993, we got this sort of weird warming that looked a little El Nino-ish. Their model did not predict that. It also didn't predict the 94 or 95 moderate El Nino event. But it's these sort of missed forecasts that give you an opportunity to think about, how your model could be better and go back and make those improvements. So there have been improvements over time to this system. When we got into 1997-98, a really important tool that was being used for El Nino predictions was starting to be these global coupled ocean atmosphere models. These models are very much the early family of the models that we now use for climate change projections, seasonal climate forecasts. These are forecasts that were actually issued in 1997. So this set here that was issued in March, it was actually issued in March for these 3-month seasons, March, April, May, June, July, August, September, October, November, suggesting this development of a pretty strong El Nino event. This is what was issued in June and then in September. So a continuing confident forecast for a very strong El Nino to develop. And it wasn't just this model, the official forecasts that were issued by NOAA, Climate Prediction Center, which was then the National Meteorological Center, was pretty accurately forecasting the strong magnitude of this event by the middle of 1997. So it actually looks like we've got a pretty good handle on El Nino prediction. Where's the challenge? We can predict El Nino, yes or no. What else do we need to know? And obviously the answer is quite a bit, or they would have given me a lot less time on the agenda. So the structure of my talk in this limited time will be to talk about, at least for the predicting El Nino events, some of the outstanding challenges that remain, the evolution and outstanding challenges for then forecasting the related climate impacts and doing something about it. So this is today. These are the skill of the current state-of-the-art forecasts, at least in the US. Michelle mentioned the North American Multi-Model Ensemble. And this is a map of the skill of that collection of systems for wintertime sea surface temperatures. So this is showing correlation skill. You want the models and the observations to go up and down at the same time, especially the big ups and the big downs. And so we can see that in this El Nino region, that's where we have the highest skill. That's great for El Nino. Of course, Michelle was talking about the importance of West Pacific temperatures, which has very low skill in this collection of systems. Other parts of the global oceans that we know are related to El Nino, such as the Indian Ocean, medium skill. And there certainly are many parts of the global oceans that are not predicted very well at all, even with a fairly short lead time. So there's a lot that we can say about this El Nino region, but there's still a lot that we can't say. And there are things that can be done better. So I refer to these models predicting El Nino, but really it's a prediction system. It's not the models all by themselves. This is sort of like a three-legged stool that supports prediction efforts. We definitely need good models, but we also need good and complete and sustained observing networks. And we need these data assimilation systems to put these things together. So when we're making a prediction, especially for the evolution of ocean temperatures, we want to start with that ocean state as close to the current observations as possible. It's that information in the ocean state that's going to evolve forward in our models and tell us what happens in 3 months, 6 months, a year from now. But the models aren't perfect. The observational networks aren't perfect or everywhere. So we use these data assimilation systems to put together our observations in a more complete way and in a way that's consistent with how the model sees the real world. And that then becomes our initial condition for our forecasts. None of these things are perfect. So when we talk about the modeling challenges for El Nino, I'm really referring to all of those building blocks. And in the modeling challenges, there are a lot of them. There are challenges dealing with the model biases. That's the errors in the model's mean state, average conditions. There are models and imbalances in this ocean atmosphere state estimation. That sounds like a lot of jargon. But what this is basically those initial conditions and being able to piece together our spotty observational network into something that's more coherent. And then there are challenges ahead in better representing processes and variability in those models. And there are actually much longer lists, as you could imagine, under all of these things. I've just listed a few of some of the more relevant ones for El Nino prediction. And even for those, I don't have time to go through everything, so I'm going to hit on just a couple of examples. One is the importance of dealing with both model improvement of these mean biases as well as the data assimilation problem. So this result comes from ECMWF, the European Center for Medium Range Weather Forecasting in the UK. And what's being illustrated here is the improvement over time in their prediction system. So this graph is showing the root mean squared error, so basically the average error of the forecast system for predicting Nino 3 SSTs as a function of lead time. So as we try to predict farther out into the future, that error grows. And this is system 1, system 2, system 3. So we can see that as those systems have evolved over time, the error has been reduced. In practical terms, what that means is that the error we would have reached after 2 months of forecasting into the future, it now takes about 3 months to reach that. So a decade of investment in better models and better visualization systems has bought us basically a month of accuracy and forecast skill, which might not sound like a lot, but if we're thinking about early warning, early action, it's a lot. Now, where does that actually come from? Because modeling centers are improving their models all the time, new data assimilation systems are being developed and tested. And at least in this analysis, what they suggest is that the total gain in accuracy or reduction in error was contributed equally by improvements in the model and improvements in the ocean initial conditions or improved data assimilation. Now, there are some modeling challenges that are just really persistent and extremely frustrating, I think, for all modeling centers. This double ITCZ has been there since coupled models came on the scene. They're still there. And there are a number of attendant model biases that are very likely related to that. So what is the double ITCZ problem? I'm sure some of you are asking, what is the ITCZ in the first place? The ITCZ is, that acronym means Intertropical Convergence Zone. And what that is a band of heavy rainfall that extends pretty much around the tropics, but we see it here in the Pacific being just north of the equator and extending across most of the Pacific. So these are the observed precipitation field. This is the observed precipitation field over the Pacific. Here's South America, Central America, Australia's over here, and the equator runs through the middle. So this is the ITCZ. It's this heavy rainfall band just north of the equator that extends most of the way across. There's also heavy rainfall here. This is the South Pacific convergence zone, but we can see that in the observation that doesn't really extend beyond the Central Pacific. Related to that are the sea surface temperatures. So these are the average sea surface temperatures from observations. Here's the warm pool. This is the average conditions, most of the warm waters over here near Indonesia in the West Pacific. And we have this area on the equator where it's relatively cooler than the rest of the tropical Pacific. This is the eastern equatorial cold tongue. And these things are related. So the winds connect the response to the sea surface temperature to where it rains. if we look at the collection of coupled models, sort of state-of-the-art coupled models, these results are from the collection of models that contribute to the IPCC. So those are basically the state-of-the-art models. They're effectively the same models that we're using for seasonal prediction, though in a slightly different setup. So these are the collection of models that were contributing to the 4th assessment report 10 years ago. These are the CMIP 5, the collection of models that contribute to the 5th assessment report. So we think of this as evolution in models, but there's 20-something models in these groups. And we can see here, so in both cases, that, all right, there's some evidence of the ITCZ, but there's also this ITCZ South, which is basically the Southern Pacific, South Pacific convergence zone that now is extending all the way across the Pacific, and this is what we're calling the double ITCZ problem. Has not gone away in CMIP 5. Related to that probably is this cold bias that we see in the equatorial Pacific. And some of you might say, because this is certainly the kind of thing that I say, well, models, all the CMIP models are not that great. We can't, maybe we're getting these maps from a couple of really terrible models, but if we look at the 5 best out of that few dozen models, the 5 best have the same problem. So it's not making it go away. And this problem with this error in the mean state of the rainfall fields, the SST fields, is actually then connected to our El Nino predictions and errors in those. So what I'm trying to draw your attention to here is a westward extension of the warm anomalies associated with El Nino. So if you look at the observations, this is from the current event. These are observations. These are all the forecasts that go into that North America multi-model. The warm anomalies stop pretty much right near the date line, whereas this collection of prediction systems actually has the warm anomalies going much farther west, and in some cases actually extending all the way across the Pacific. This is a challenge. But there's something that we can say about El Nino prediction. We have some useful information. We have some idea of where the challenges are that could be addressed to make things better, assuming that we can address those. What are we going to do about that information, assuming that we can get better El Nino predictions, that it's not just yes or no? This graphic here this type of graphic has been referred to a number of times already. It's our expectations of climate impacts during El Nino events. And what we do know is that these impacts have seasonality associated with them. They tend to happen at a certain time of year. But we also know that these expected impacts don't happen in every El Nino event. So what this is not telling us, though, is even if we have just, all we know is we're having an El Nino event, yes or no, this still doesn't tell us in any one of these expected impacts what's really the risk or likelihood of these impacts to occur. And then given the particular details of this El Nino, how are these expected impacts changing? And that's where some of those challenges, and this has been referred to by Adam and others, this is some of the challenges going forward in how we predict the regional climate. And we have learned quite a bit since 1997-98. I'll draw your attention first to this lower graphic here. In 1997-98, really the focus was on predicting the SST in the tropical Pacific. Even though we were using these global models, we really just wanted to get the El Nino right. We really didn't care too much about what was going on in the other tropical oceans. And when we applied these sea surface temperatures to atmospheric models, it made it dry over East Africa. Whereas our expectations would have said, October, November, December, we should be expecting wetter than average rainy season over East Africa. So what's going on here? We have since learned that it's actually these related sea surface temperature impacts. So the fact that the Indian Ocean tends to warm up when we have an El Nino event, that's important for then capturing the regional precipitation response. So one thing, a very important thing that we've learned in predicting the regional impacts is everything is not driven by El Nino explicitly directly. There are often very important connections to other parts of the global ocean, and it's those regional sea surface temperatures that they're then driving regional climate anomalies. We also know that improved model resolution can help a lot in our realization, our modeling of regional climate anomalies. So what's shown here is during El Nino events, the typical response in precipitation at the top from observations, or this is sort of the Indonesia region in the Americas. This middle panel are 50-kilometer model resolution. That's a fairly high-resolution global model, and below 200-kilometer model resolution, which is something much more akin to what was being run during the 97-98. And we can see that while the broad gross patterns might be captured even by the low resolution, they're improved, still not perfect, but improved, and the local scale details are definitely brought out. And if you're going to start to then bring in the subtleties of better El Nino prediction itself, you better start off with models that are capturing the gross characteristics of El Nino response. So then what are we going to do about it? Meaningful climate information is one critical starting point for a lot of action. But that's not enough. We need to translate that into what it actually means in terms of impacts and translate that into meaningful action. So I'd like to show two examples, one on disaster risk reduction and another one on agriculture. This one here, with work with the International Federation for Red Cross and Red Crescent, happened some time ago, so we actually have some conclusions on that. The agriculture example is really in progress and an exciting starting point. So in this case here, this wasn't an El Nino event, but what we were looking at was a rainfall forecast for the Sahel in West Africa that showed that rainy season could be extremely heavy, extremely above average. And certainly the humanitarian organizations were very concerned because 2007 had been an extreme season in the region, and there had been a huge loss of life and loss of property. So working with the International Federation of Red Cross and Red Crescent to understand what seasonal forecasts meant, how to interpret those, working with other sectoral scientists to translate that, say, into river forecasts, flood warnings, and actually mobilizing resources through the Red Cross Red Crescent. This is the first time ever that the Red Cross applied for aid in advance of a disaster rather than in response to one. And they got that, they got those resources, and they were actually able to prepare somewhat. And that worked. So they were able to respond much more quickly. There was a dramatic reduction in the loss of life, and also a pretty substantial reduction in the cost of that, of addressing that disaster. For agriculture, I'm going to bring it to 2015. This is some work that we're doing with Uruguay, with funds of the World Bank. Walter Baitkin is leading this work. And so if we look, starting into 2015, what these little, this is Uruguay through time, looking at soil water balance. And so this is January coming up through April, weekly maps. And what we see is that the evolution of drier conditions as 2015 was unfolding. In the April, May, June season, we had a rainfall forecast that was suggesting that at least the northern part of the country was likely to continue experiencing below average rainfall. And this was putting a lot of, this was adding a fairly bad forecast to a lot of already vulnerable areas. So places where the vegetation was low, places where the water on the ground was low. And because cattle is so critical in Uruguay, what is it, something like 5 cows to a person? The cattle resources are a major vulnerability. In Uruguay, you don't want to put them in harm's way. This is where the stocking rates are very high. There's a lot of cattle and livestock in that area, and this is the part of the country likely to be hit by a continued drought. And so this type of information, the monitoring and the advanced information gives a much more objective and transparent way for the government to react, to prioritize assistance, and to make better decisions going from one bad situation into a potentially worse situation. Now we're looking towards the end of 2015. As Adam pointed out, this is a part of the world, here's Uruguay. This is a part of the world that tends to experience heavier rainfall in their summer during an El Nino event. But Uruguay is a relatively small place on the global map. It's only a couple grid squares. So working with the climate scientists and agricultural scientists there to help them refine their climate information. And then that can be fed into this type of information for a better preparedness in advanced warning. So in conclusion, in predicting El Nino events, yeah, we can actually predict the existence of an El Nino event pretty well. But there's a lot that could be done better, and that includes the timing, spatial pattern, the diversity of El Nino events. We heard that they're not all the same, and the uncertainty in what actually evolving or being strong. For forecasting and related climate impacts, we do need good quality models, but we also need that analysis and tailoring to translate what the models are saying into a real on-the-ground risk or likelihood of those climate impacts. And then we need to do something about it. And that's where the wealth of the expertise in this room is so important, is getting to this doing something about it part, because the good climate information is a starting point, it's not enough. Turning climate information into socioeconomic impacts that make sense to the rest of the world and meaningful action that people are actually going to get behind is not something that the climate community can do on their own. We need this entire community. Thank you.